It's awkward. Okay, so good morning. It's 11:50. I know it's weird. It's weird. You probably already eaten lunch and it's still morning. I ate lunch at like 10:30. Makes no sense at all. Yeah, Lauren, that's what I was thinking too. We know that this has how many vertical asymptotes? It has 2, and they are at x equals 2 and x equals -1. Anytime we're talking about asymptotes, it's got to be a line, so it has to be x equals a number. If you don't just give me a single number, please. So, of course, we're looking for the behavior near these, which means we're taking the limit as x approaches. Let's go from left to right, meaning we're going to start with -1 from the left. We're talking about f of x, so in other words, how are we going to figure out this out? Yes, Lauren? For instance, yeah, really, really, really little bit. For instance, are we good with that? 0, 0, 1. That's pretty close. Oh, 0, 0, 0, 1. You want to go there? Are we ready to do the 3 zeros? Okay, now this just happens in your head when you plug in -1.0001 at the top. Basically 2. Like significantly it's 2, and even at close to it gets -1, it gets even closer to 2, doesn't it? But that's not going to change much. This one? Like, it's about around 9. Around 9. This one? Tiny positive negative. Negative, right? -1.0001. So we have this positive with a tiny negative. We're going to negative infinity. On the other side of this, as x is going to -1 from the right, this limit is going to. So in this case, it won't be -1.0001. This is going to be 0.9999. I think it makes a difference here. But it suddenly becomes a tiny positive. Divided by a tiny positive, the result will be infinity. So what's happening here is we have like, no, I'm sorry, it's 2 on top, isn't it? 2 and then like 16 and then like a 0.0000. And this gets big, like it's not bigger, but smaller and smaller as you approach 1 from the left. So this number here is counting this to go to. There's tiny numbers in the denominators. Of course, we have 2 more. The limit as x approaches 2 from the left. In this case, we're talking about 1? No, that's so far from 2. 1.99999. Around 0. Like a small positive. Tiny positive because of the square. And this positive infinity. Just looking at trends there. And the limit as x approaches 2 from the right of f of x. Does anything change there? Not really. I think it's still positive infinity. Any questions about those? Okay. Homework. You saw that there were 2 different ones? Sorry about that. I'm going to try to consolidate that. Hopefully you're able to finish that within an hour. If it's taking significantly longer than an hour, please let me know. Unless you're like distracted at the same time. If it's taking significantly longer than an hour, you happen to be on Snapchat at the same time. Let's be real here. And I don't know. The homework shouldn't take you much longer than an hour. In general, it shouldn't take you longer than an hour and a half. It doesn't usually take that long. So if it is, please come talk to me. Let's figure out what's going on. Let's streamline some of that and get you out. So you're not suffering so much. Even though we all agree that more homework is better, right? Especially math. Especially math homework. It's not that we don't want to have to work so hard for each individual piece of it. So keep it in mind. If you think you're spending too long on the homework, let's talk about it. We're going to continue our study of functions today. Now with looking at limits near vertical asymptotes, but we're going to see what happens to functions as they approach infinity. And I know we've done this before, but it's going to look a little bit different today. So block 6. Oh my goodness, I lost it. I'm going to make sure I'm still recording. Okay, 6 minutes in, I'm still recording. Good. So today we're talking about horizontal or oblique asymptotes of rational functions. So this is page 16 right there. Oh, Mr. Moore. Yeah, so we've spoken about horizontal asymptotes. Where have you seen them before? What kind of functions have you seen these in? Do you remember? What's that? Oh, 1 over x. Exactly. It's one kind of rational function. Where else? Exponential. Nice. Yeah, those are the 2 we've seen. So yeah, like 1 over x. Y equals 1 over x. Can you all visualize 1 over x? I hope so. It exists in the first and the third quadrants. Let's look something like this and something like this. And why does it have a horizontal asymptote? Julian, what is it you said? Exactly. As x approaches infinity, the values get close to 0. Never actually hits 0 in this case. Also, as x approaches negative infinity, the value is approaching 0. Of course, for very small values of x, the whole value go crazy. That's a tiny number. 1/2, that's kind of tiny. That's hard to blow out. Negative 1/10. 1 over 1/10. That's already negative 10. But as we go to infinity, that's where you start seeing horizontal asymptotes. So you're going to see things today that look like, okay, let's say that's our horizontal asymptote. So just a general idea of what we're going to be doing is we don't care about what's happening in the middle, but in the end it's going to even out to be something like that. And usually it's the same thing on the left and right. So if we see this, it's going to even out to be this. That's what a horizontal asymptote does. And we get it just by looking at the behavior as x goes to infinity and negative. We don't care about what's happening. It's going to be craziness, just like with that 1 over x. So for horizontal asymptotes, you're looking for limits as x go to infinity or positive infinity. For oblique asymptotes, have you heard of oblique asymptotes before? You're saying, what is that? The word oblique, could you show me what that means? Can you show me a visual? Those of you know? Seems like some of you know. Oh, somebody here. Somebody here.
Is that not muscle?
Maybe that's another one. What is that?
Is that not muscle? Like a muscle?
Oh, oblique. Yeah, oblique muscles are right here on their sides. You may have heard it in geometry. Have you heard of oblique pyramids?
Yes.
Did you hear about that?
A little bit.
Like maybe just one sentence of oblique. Maybe. What is an oblique pyramid? Yeah, it's when it's not standing straight up. It's like if that vertex is not directly over the center. It's called an oblique pyramid. And generally, we don't study them much in geometry, but they may have been mentioned in passing. So oblique asymptote is not an asymptote that looks like this. It looks like this. right? It's tilted. It's also what's called a slant asymptote is often how I'll refer to it. You may refer to it however you like, either slant or oblique, but I'll put on here that it's also slant asymptote. So what that would look like is, here's our slant asymptote. These only come from rational functions, so we may have a vertical asymptote here as well. So behavior at the vertical asymptote is exactly the same as what you're used to. But do you see what's about to happen? For that other asymptote, it's going to approach it just like it would with others. Something like that. That's its general behavior.
What, like a horizontal asymptote also?
Well, this is horizontal asymptote. This is the oblique asymptote. This is the vertical asymptote. It will usually be a vertical asymptote because it's rational. But let's finish this graph up. Do you see where the rest of this function would go? Yeah, it depends. It depends. Like if my vertical asymptote is happening here, you see what's going to happen? Do this kind of thing, right? It'll do. But it just eventually has to adhere to that oblique asymptote. And we'll talk about how to find it today. What happens when you're near them? Get across them. Let's see. So does that make sense about that? That's where we're going today. We're looking at functions. We're just trying to check the behavior, not close to the vertical asymptote, but the last time. We're checking to see what happens away from asymptote, positive, negative, infinity. Well, we get right into it. Find the horizontal or oblique asymptotes of the functions. Describe the end behavior using limit notation. Okay. Before you do anything, just put your pencil down. If this were a polynomial function, that's 2x that's alone, you can show me the end behavior of that. This is not just a polynomial. And you don't be up here and down here because
Positive or odd?
yeah, this is positive and this is odd. Do you care about this? No. Do you care about this? No. Not in a whole heartless way. We care about it, but it just doesn't have any effect on end behavior. Eventually, as x gets larger in either direction, this is what happens, isn't it? In the middle of this main vector will go up and down. Eventually, that will be equal. This bottom one, if it's just this polynomial, same thing. It's going to be this. We don't care about this. We don't care about this. Not in the heartless way. We don't talk more like that. I like that. But we just really care about the leading coefficients. So what I'm saying here is we're looking at this overall as x is going to infinity, x is going to negative infinity, right, Ellen? As it's getting bigger and bigger and bigger, these lesser terms kind of fall away. So we could think about this function as 2x cubed over 3x to the 7th. Of course, they're not the same, but when we're talking about large values of x, it kind of amounts to this, which can be simplified too. 2 over 3x to the 4th. What happens to this as x goes to infinity? What's the value of this as x gets bigger and bigger and bigger?
It's small.
It's smaller, doesn't it?
Yeah.
How about as x goes to negative infinity?
They're the same thing.
Negative infinity.
Or negative. Oh, it'll still be the same range. Yes, because they're more
It's still going to 0, right? That 0 is our horizontal asymptote. So just visually speaking, we don't care about what's happening in the middle, but we know that eventually this is going to settle down to be pretty close to 0. On that side, it will settle down to be pretty close to 0 here, making a horizontal asymptote of y equals 0. Because when you plug in a 10, here, you have like 2,000. You see how this minus 50 is? It's minimal. And then 1? Who cares? And look at this. If you plug in a 10 here, you suddenly have 3 with how many zeros? 30 million? we become insignificant. So it equals like 2,030 million. And that's when x equals 10, we're going to infinity. So what's happening is that value, so the bottom wins out. This is called bottom heavy. Whenever it's bottom heavy, horizontal asymptote will be y equals 0. So let's put all this information together. The limit as x goes to infinity of this function is equal to 0. The limit as x goes to negative infinity of f of x is equal to 0. Therefore, there is a horizontal asymptote y equals 0. Always true if the function is bottom heavy. Bottom heavy. Yeah? Go ahead and discuss that second one. That one right there. Okay, so did you get the limits?
No.
Is this bottom heavy or top heavy? Neither, right? They're equivalent in terms of power. So, yes, the terms will fall away, the ones of lesser kind of importance. That's not nice of me to say, not importance. Lesser degrees will fall away, leaving us with these two leading terms battling it out. So this would just result in negative 1/3. So again, when you plug in 1,000 over here, these all won't happen. 2,000, or that would be 2 million, 1,000. 2 million versus negative 6 million. Negative 1/3. Negative 1/3. 2 billion versus negative 6 billion. Right? They don't completely cancel out, but the quantities cancel out. The coefficients become important. So the limit is, for both of them, negative 1/3. Which means in this case, we're not looking at a function that's tending to 0. In this case, no matter how big we get, those numbers will tend to a particular number, 1/3 in this case.
Is this always true again without the access on the top?
Yeah. You mean if it's the same?
Yeah.
Yeah, it's the same degree. So, how would you summarize this? If it's neither bottom or top heavy, horizontal asymptote where? Y equals, in general, negative. In general, we just take whatever number we got right. If this is a 5, this is a 23. Yeah. Oh, that's interesting. Thank you. That's very poorly done. Negative 1/3 has a specific place, and it's definitely below the x-axis. Oh my goodness. Good catch. That's definitely extra credits right here. Right here. That counts for something. Yeah, when you see something like that just doesn't make sense, please let me know. Sometimes I'm on autopilot. Like that. So we say that, therefore, horizontal asymptote y equals negative 1/3. And make sure to put that negative 1/3 for both x-axes. Julian, what did I do?
I just want to
Oh, okay.
Why would both
Oh, it could be below. We don't know. I'm just talking about it. But you're right, we're going to do something closer examination. And we could, if we had a little bit more information, if we had a vertical asymptote, which I think we could get, find out where is it coming from. Maybe it's coming from down here. It's going to be this. But I don't want to think like that. Is there another question? Okay, let's keep going. Hey, look at this next function. Are you surprised that it is... You notice immediately that it's top heavy? Okay, I'm going to need a minute to discuss what's going to happen here. So of course you took away all the fluff, didn't you? That only happens when X is getting very big, very small. Don't do it when you're like taking it as X goes to 2. These are quite important X is going to a finite number. But yeah, this which this becomes notice I'm not putting an equal sign there, by the way. It's just kind of logically that resembles this, which is equal to 3x. So what happens here? Well, it is definitely oblique, and we know that because it's top heavy. It's top heavy, and it's not a horizontal line. As x goes to infinity, what's happening to this value? It's increasing. It's getting bigger and bigger. As x goes to negative infinity, it's smaller. Smaller to 0? No. It's hard. Smaller is a hard word in math, isn't it? And what do you mean by small? Negative infinity. So just like a cubic would do, like up to infinity, down to negative infinity? Yeah. No, it's not a straight line. It's a straight line, man. Let's say we're going to use a slant asymptote. So the question is now, what is a slant asymptote? What is that linear value?
Why like the curvy?
Oh, 0. We have to use one of your favorite things to do in all this mathematics. Isn't that it? So we do some division here. You just add 0. Long division. I see it. The ice is shiny. Or that might be the
tears. I think they're tears. That's why they're shiny. That's what. Yeah.
Why can't we use the division here?
No.
X can't. You pick 1 to 0.
Because it's not like the X minus 3.
Right. If it's just X minus 3, then please use the division. But it's cubic. You can't use the division for anything other than linear. And even that's kind of iffy. So let's see if you remember how to do this. Can you fit it in here? What even goes inside the division sign? Which, the top or the bottom? Yeah. Don't forget, 3x to the 4th power. What's next? Plus 0 x cubed. Could you say minus 0 x cubed? That's fine. I think that's weird, but it's also weird to add 0. Minus x squared plus 0x plus 0. And on the outside, of course, plus 0x plus 1. I'm going to need a minute to see if you can piece this amazing experience together.
Yeah, I don't want that.
Maybe we can discuss the part of
How many times is this first step?
Do you do this step one?
You can regulate. You don't want to regulate from the tear, the water.
I know.
Tears of confusion. It's okay. They'll go away once we figure it out.
Okay, let's talk about the first step. We have to figure out how many times the sole polynomial goes to the sole polynomial immediately? No. All we're going to look at is unit coefficient. How many times x cubed is going to 3x4? In other words, x cubed times what equals 3x4? And the answer to that is 3x. We take that 3x and do what with it? Put it on top, and then what? Multiply. Right, multiply by the entire divisor. So the whole thing. So 3x to the fourth minus 3x cubed plus 0x squared. Did I do this right?
Wait, why 3x times 0x cubed? Wouldn't that just be 0?
Yeah, 0x squared. I want to keep my place values.
So the
This times this.
oh, sorry. I thought you were trying to.
I think we're okay. But the next step is to do what? Subtract. I think that's what you're talking about. Right, from here right, it's exactly the division that you remember from elementary school on steroids, so right, we have x's involved here. So we subtract. Oh no! So this becomes 3x cubed minus x squared minus 3x. Don't forget to bring down the 0. Are we done?
No, it's not.
You're not done until this is of a lesser degree than this. We do go through the process again. I'll give you a chance to finish it. Who's already finished? Okay, so 3 of you are finished, but let's give everyone else a chance. Okay, I'm kind of scared because I don't know. Oh, yeah.
My bad.
Sorry, no.
Wait. What is
You getting it? You getting it?
I got it, but like, it just brought it back.
Traumatic?
Yes. I didn't do well on this time, so I was like,
I'm here to support you, emotionally, academically, whatever you beg. Okay, next step, you ask yourself, how many times does x cubed go into 3x cubed? And the answer for that is 3. So I'm going to put
minus 3.
plus 3 here first. Are we good with that?
Yes.
All right, just the question is asking x cubed times what equals 3 plus 3. And now we take that 3 and distribute. So it becomes 3x cubed minus 3x squared plus 0x plus 3. And we are subtracting all of this, just like regular long division. Which results in 2x squared minus 3x minus 3. Yeah, be careful with this subtraction. Notice that what we have left is of a less degree. So this is called the remainder. What is this called? That's the quotient.
the answer to it.
So you just took like 3x plus 3 and then in another parenthesis, like multiply.
Yeah, so let's see what this means. Let's summarize all this. What we've just found out is that our original function is exactly equal to 3x. Is it exactly equal to this?
No.
How do I write the rest?
R 2x
Plus
minus 3.
2x squared minus 3x minus 3 over
No. X cubed. X cubed minus
x cubed minus x squared plus 1. This is like mixed number form. Right? When you're doing mixed number, it's that number and you write the remainder over the original divisor. Exactly the same thing. What would happen if we took the limit of this portion as x goes to infinity? It's bottom heavy, so this limit would be to 0. We could go right to infinity. I didn't try it before I say this again, but it's kind of important. Okay, so we calculate this equal to this. This portion as x goes to infinity is equal to 0, which means as x, the very large value of x, this function is basically this, which is our partial portion. This is our oblique asymptote. It's never going to be that line. It's going to be adding something, and that something is going to be added to it. It's getting closer and closer to 0. So this is, right here, our oblique asymptote. So the oblique asymptote, I'll just abbreviate OA, is y equals 3x plus 3. Yes, sir. Then you haven't gone far enough. This is practically right. No, by definition, it's got to be right. Because it's more than you keep dividing, yeah. So, wait, the quotient flows. Wait, there's one qualification. Notice how much heavier the top is. It's heavier by 1 degree. That's only gets to 50 feet. If the top is heavier by 1 degree. So that would be exactly this with a line. If this were heavier by 2 degrees, you have a parabolic asymptote. What? That's out of the scope of this class, really, but it is a thing. In fact, if you look at the next problem, you'll see that not only is the top heavy, parabolic, parabolic asymptote. I like it. Yeah. So, all right here, oblique asymptote happens when function is top heavy by 1. And I hope that has meaning to you. I hope you have enough room to write in your notes too. Squeezing it in. I barely have enough room here, and I have like a whole lot of space. Okay. What I'm about to do is going to upset some of you. This next portion. Like it may go against everything you believe in. And first of all, let me see if I can actually make this. Boy. This recording thing is not my friend. Asymptotes! You may have been conditioned to believe that they can't be touched. And it's true that vertical asymptotes cannot be touched, but horizontal asymptotes, touch away. Touch away. And what I mean by that is they can be crossed. right? And that may not sit well with you. I understand. It might keep you up tonight. But first of all, why can't vertical asymptotes be crossed? Why can't the vertical asymptote be crossed? Enzo, I want to hear what Enzo, what do you think? Because it's undefined there, right? And that gets what you were saying, right? That it just wouldn't be a function there. So how would it possibly even cross that vertical asymptote? But a horizontal asymptote just happens when x is going to infinity, negative infinity. So let's say that we're over here, like obeying that vertical asymptote. What's saying we can't just cross that one? Nothing. All that we know is that eventually it's going to have to come back and adhere to that horizontal asymptote. So it could be crossed somewhere when x is small. And when I say small, it's relative. It's relative to infinity. So usually between negative 10 and 10 power times. But yes, so very often that the horizontal asymptote will can be crossed. I'll say yes. Okay. Yes. You have to be a genius. You have to be a genius. So you all will know, and algebra will tell you how many times. But let's do this. Oh gosh, this moved again, didn't it? Really? Yeah. 1, 2, 1, 4, 6, 4, 1.
Yeah, I know you're.
That's what I'm saying. No, it's like
Yeah, I know.
Are there any questions? Can you please do this thing? Can you sketch a graph of a rational function with 2 vertical asymptotes and 1 horizontal asymptote that crosses horizontal asymptotes?
Yeah, there's a little bit of chatter right now. There's a little bit of a chit chat right now, so let's squelch that. But just as an exercise, it's a graph of a rational function with 2 vertical asymptotes, 1 horizontal asymptote that crosses its. And the function that crosses its horizontal asymptote 3 times. So let's do this. Let's start this together. We'll have 1 vertical asymptote there, 1 here. You want positive or negative horizontal asymptote? You guys are such nice people. Okay. Can you make a sketch of just a graph? We're not going to attach any sort of algebra to it at this point. Can you sketch a function that would cross its horizontal asymptote 3 times? And still adhere to all the vertical asymptotes.
So we haven't drawn it.
You haven't drawn it. So I don't know what yours looks like, but let's say that you're approaching that vertical asymptote on the left like that, such as it's going to negative infinity. Do you see how that would cross the horizontal asymptote?
Yeah.
Right, it would go up and then keep going up?
I mean,
No, it has to go back down. That's what the horizontal asymptote does. It's like gravity. It just kind of pulls it. It is, right? It just comes down towards it. It might cross it again. Yeah, it might cross it a couple of times. Or it might do something like this.
Wait, what is it? Wait, why does it come back down again?
It's just saying it could. It could.
So it doesn't act like absolute.
I mean, it will. Right, because by definition, the limit as x goes to negative infinity is that horizontal asymptote. So it will be attracted to it at some point. That's right. And then the graph of speed Could say the whole question again? Did the graph be speed between the 2 vertical asymptotes? I think the assumption here is that it's defined everywhere except
for those two vertical asymptotes.
Well, I want to do the whole thing, but yeah, I guess right now we have 2 already. Let's just supersize this. Let's say that we're coming down from here. And so there's the vertical asymptote. You see how it's going to cross the horizontal? How many times is it going to cross it?
As many times.
Can you imagine 100?
Yeah, as many times.
Can you imagine just 1?
Yes.
Okay, usually you'll just see 1 there, so it would look something like this. But I think you guys were imagining this, something like this, right? Which is perfectly fine. I'm just saying, what if? It could... I'm trying to break your preconceived idea that asymptotes can't be touched, because you're right when it comes to vertical, but horizontal, touch away. As many times as it wants. Facts. Yes. Yeah. Yeah. Yeah, it could be craziness. In fact, there is one function you're going to be dealing with a little bit later this year, actually, that's going to have... It's going to look like this. It's like an asymptote is equal to 0. And it crosses infinitely many times. Oh my gosh, what happened to it? Right, it's a guide. Right, the function is... You see how here it's approaching 0, and at the same time it's hitting it infinite number of times? But
you would still say that asymptotes 0 or whatever, even though it directly touches.
Yeah.
I thought the definition is that it's a number you're not supposed to read.
It's more of a number that it approaches.
It approaches
Right, it's approaching 0. You can see with the numbers, there's maybe 1, this might be -1, but it's only 1/2 and -1/4. And those values are getting closer to 0. It's a guide. Or the oblique as well. Yes.
On the sketch of the view, it's like you can draw something and like the function doesn't
That's what horizontal. The thing is, on the test, it's not going to be so freeform. It's not like, picture this. It's going to be draw this function. I give you the function, you can say, oh, here's the horizontal asymptote, here's the vertical asymptote. I'm going to find out where it crosses the horizontal asymptote, if it even does, etc., etc., etc. It's going to be very specific.
You just plug in the
We're going to look at trends. So the idea is to never plug in. We're not trying to get specific values. Like notice I often talk about just positive, negative, not caring about the number. We're going to continue that trend, not like make an XY chart. That's always the last resort before everything else has been exhausted. Oh, yes. So this problem, what do you recognize? This first one. What are the 2 words that come to mind? Bottom heavy. Second one, what do you recognize? Second one? Equal. Equal in powers. I wish there was like a middle heavy. That doesn't make any sense. Okay, not heavy. Yeah. So try these examples here. If you want to take this time to stretch or check your Instagram, oh, right now. So, I thought you were
Oh wait. Yes. No, this was
oh, yeah.
right? Okay, I just missed it.
So every single one.
It's on the home. Okay, if you look at it.
Yes, so when you go to this one, you're right. You go. So, that's how we do it. Yeah, search. Just activate. Yeah. It almost seems too simple.
I do expect you to be back to grind. Okay, so you should be working on these 2 problems if you haven't already.
Has anyone finished the top 2?
Bless you.
I need about 90 seconds before I continue with
Oh, I just want to do it 0.
Okay. We're running a little bit behind, so for this first one in example 13, you'll notice that it has bottom heavy, so it has a horizontal asymptote of y equals 0, yes? Oh, I'm sorry. There we go. I forgot I had frozen it. Yeah, y equals 0. Cool. It's also asking find where it intersects the asymptote. So how do we do that? We set this equal to 0. You just see where's the function equal to 0. Now, next step would be to do what? Multiply the denominator, understand that in the fraction, if you want to set it equal to 0, you just have to set the top equal to 0. So it shouldn't be too difficult to solve this. If you can get through this, I'd be very happy. So x equals 1/2. So the coordinate that it crosses through would be -1/2, comma, 0, of course. Yes? We notice in the second function, what do you notice first? Same degree is therefore neither top nor bottom heavy, therefore middle heavy, therefore there. What's 3? Horizontal asymptote. That's what I'm looking for. We're getting to the good stuff. Y equals 3. It does actually cross? Let's see. 3x squared plus 2 over this. I just set this equal to 3. I just set the top equal to 3. Does that work for this? No. No. This is different. Multiply both sides by that denominator. So 3x squared plus 2 equals 3x squared plus 12x minus 15. Oh, this is nice, isn't it?
Wait, why would you do it?
Did I do it right?
Right, but not
I multiply both sides by that denominator, so the denominator cancels.
Wait, yeah, but why do you do that for the left side?
Oh, you could.
But when a fraction is equal to 0, all you have to do is set the top. 0 over whatever.
It's the same thing. 0 over x.
But you're right, it is the same thing. Good. So these cancel out, and very quickly you see that x equals 17/12.
So yeah, so it crosses the line, the horizontal asymptote at 7/12. You get the y value, so I plug that back in. No. We already know it's 3. You can say with a lot of time trying to other coordinates, we already know y equals 3. If you're plugging in this number, you're probably doing 1.
And waste a lot of time. So be mindful of what you're doing. So 17/12, comma 3. Oh, what do we notice about this one? It's oblique. So it's definitely oblique. So we have to find the oblique asymptote. Did you do this already?
Yes.
So the oblique asymptote here is just plus 0. Is that right? How do you do that? Plus 1? How do I do this? Should I do long division?
Yeah. If you want to.
Oh, yeah, it's minus 1. It's minus 1.
Oh, we put a positive 1 here, excuse me. Positive 1 goes right there, then we have 3, -2.
It's divided like
If we wanted to, why would you put that in when it's impossible?
So we just found out that this is equal to 3x plus 1 plus 2 over x minus 1. Right, the equivalent. Are we good with that?
Yeah.
Now what happens to this little piece if x goes to infinity and negative infinity? This piece goes to 0, doesn't it?
Yeah.
Therefore, for very large values of x, this function is basically
Y equals 3x plus 1. Oh, y equals 3x plus 1, of course. Does it cross it?
No.
No? You can't? Who told you this?
Yeah, like,
I don't know. How do we figure it out?
why couldn't you?
No, you need to
Exactly. Why couldn't you? How do we figure it out?
use the x plus 1.
Yeah, just set the function. We're going to see, does this ever, remember this is a y value here. Does the y value here equal the y values for this function at the same x value? So is there x value that gives the same y value? So I think when we work this out, 3x squared minus 2x plus 1 equals 3x squared. Oh, this is a binomial, be careful. So we have negative 3x plus x minus 2x minus 1. Did I do that right? Can we solve for x? We could. If there were any x's remaining. Yeah, we have 1 equals negative 1. Is that true?
No.
Check the number line. Is it true? You sure? Okay, it's not true, which means it's not going to cross that oblique asymptote. No intersection. But could it? It could. I'm going to tell you it's unlikely, but it could. I want to show you just a visual of what we're doing here. Did I do this? Will this work? Why won't you switch? Yes. Yeah, but it'll be the same thing. Yeah. Okay, so this is the function that we're talking about. Notice that vertical asymptote right there. Do you see that it has a slant asymptote? Like you see that visually, but also here's the slant asymptote. So you can see it's really approaching them very, very nice. Oh, that's from my recording. I think it just records now.
Oh.
Yeah, that's awkward though, for sure. But you notice, I think there's one more question. Do you see where this is on your worksheet? This is back to the last page.
Yeah.
Yes.
So this is where the top is 2 degrees heavy. I just want to grab the screen to see what's happening.
So we take out the other ones. I'm going to leave the asymptote. So they turn this off, and turn this one off, turn this one on.
Yeah, it's a lot. But I hope it makes sense for the asymptote at 1. But when it's going away from that, it's not doing what we're used to. So apparently when I do this division here, and I did that by
Synthetic, because I could, we get this parabola. And you can see, right? You see how it's approaching that parabola?
oh, because
That's the oblique, like oblique.
this is the parabolic asymptote.
But you won't get
This
the other.
because it's like yeah, exactly.
Like, so on the test, you won't get a question like,
Right. Well, it might say limit to infinity. I guess that's not asking to sketch this.
so basically, I guess you'll never be asked to find that square. In this entire class.
Probably find that x plus 1?
No, it's just the same.
Is it
Oh,
a
but yeah, I gotta find it.
It's just weird.
It's a little different. But I do want to move on to next. So this is more for enrichment here.
I have a question for you all. how time flies. Why are you going back? Why? I don't want that. Ends at 1. Yeah, I'm gonna skip this example 14 and just make some notes in here. Let's say we had f of x equals x minus 5 here. I'm gonna leave the top blank for now. What do we know about this function? Vertical asymptote at 5. Are we sure about that?
Yes.
Okay. Or do you know the domain? X definitely can't equal 5. Is there anything I can make the top such that there is no vertical asymptote, though? Yeah, what if the top is x minus 5? Ah, yeah, I studied this before. So these cancel, leaving 1, but we have to remember that still x can't equal 5. So let's think about what this looks like. If we go back to the original function and we plug in like a 7, do you see what we get?
Yeah.
How about if we plug in 100, do you see what you get?
Yeah.
How about negative 1,000, do you see what you get?
Yeah.
How about 5, do you see what you get?
Yeah.
No. You actually don't see what you get. You plug in the 5, you get nothing. So I think everything else, except for that, when you get a 1, I hope it makes sense that our graph would look like this. That feature is called, as some of you already know, a hole. Sometimes it's also called a discontinuity. Would that make any sense?
A little bit, because you're not going through that.
Yeah, like here it's nice and what's called continuous, right? There's no break there. Continuous, and then poof, it just lacks that continuity. So we call that the discontinuity there. And that happens anytime. What do you think has to happen for that to exist, for that hole? Algebraically, what has to happen? Right, a factor has to cancel. So, like, if we look at this one, f of x equals 3x minus 6 over x minus 2. First, you're going to factor out the 3. Anything cancel? Yeah, these cancel. Which means there is a hole at 2, comma 3. How do you know it's 3? Yeah, because they're all 3. Everything else is 3. Let's try a couple more. How to find a hole in a rational function? Any common algebraic factors? If yes, cancel them. A hole is left where the factor equals 0. If yes, cancel them. A hole is left where the factor equals 0. So let's take a look at this problem here. Find the coordinates of the hole or holes of the following rational functions. Do you want to factor the top or the bottom first? The bottom is so nice. It's like eating dessert first. Difference of squares. X minus 2 times x plus 2. Top, I think one of them is going to be x plus or minus 2. Or both minus.
So where's the hole? X equals 2, right? We set the thing that cancels that. We said that equals 0. X equals 2.
But how about the y value?
No, it just be 1/2.
Now we take that 2 and plug it in to the simplified function. Exactly. If we did it earlier, it would be 0. Three, 4.
4 minus 1. Like 2x.
From substituting x value into simplified. F of x.
Now, technically, 2 is not in the domain of this function yet, the simplified version. Does that make sense to you if I'm in the domain?
Yeah.
Because this just simplified version of this. That's why when you plug it in, it doesn't result in a point, close point, but it results in how big is the point?
That's small.
Yes, exactly. Okay. Would you simplify this last one? So the bottom is going to be x minus 1 times the quantity of. We just found out there's a hole at 1 comma. Do you see the 2/3? No one sees that? Just plug it into the remaining portion. 2/3.
That was a lot. We have a quiz next time. Yeah. It's on this. The first 4 days. So before you leave, what I want you to do is very quickly discuss with your neighbor. And the three of you are going to discuss now. What are the main takeaways for today's class?
How much is each quiz? How much is each quiz?
We need to go through that process. How long do you need to Okay, so what are some of the takeaways? One person at a time.
Defining horizontal and oblique asymptotes. Top, heavy, bottom.
Okay, so horizontal asymptotes. Tell me about it. They can be crossed. What else?
Top, heavy, bottom, heavy.
Top heavy. Well, for horizontal asymptotes, we're looking at if it's bottom heavy horizontal asymptotes, 0. It's 0. If it's equal, then
that's where you find the oblique asymptote.
horizontal asymptotes.
No, then
That's a vertical asymptote.
So if it's either top or bottom heavy, the horizontal asymptote is y equals the ratio of the moving coefficients. If it's top heavy by a factor of 1, if there's 1 over equal, that's asymptote, which is by 2. By 3, by 3.
an asymptote that is like probably
Okay, cool. For those of you who observe, have a very beautiful fast. Everyone, have a great weekend. I'll see you. Thank you.
Have a nice weekend.
Thank you too.
Wait, if it's asymptote,
Oh, just
you want to
one.
see, or horizontal, you want to see
Turn this off.
that's fine.
No problem.
You just use a factor then to like, and you plug in a 0. When you want to see
You
if
set
it
it equal
crosses.
to the oblique.
I see. And then you'll just see what, and it'll end up giving you what is the quiz, like just from, except from the
Oh. Today was polls, so it's gonna be actually including answer. I put my lectures on YouTube. There's a link to that on the hub.
Thank you, Mr. You.
Yes.
Thank you very much.
Thank you. Thank you guys.
Have a great holiday.
Thank you.
And the homework on the math lab, it said it was late. I don't think it's okay, great. Thank you.